from University of Lehigh, and she will going to talk about constraining non-relativistic RG flows with holography. And Sera, we are so pleased to have you among us. Welcome, and please.
Great, thank you very much for the invitation. Please let me know if you cannot hear me well, and if you have questions, I won't see you, so just unmute yourself. But it's nice to see a few familiar names on the screen. Okay, so by the way, this is a picture of Lehigh pre-COVID. I have no idea if this still looks that way because I haven't been there for months. We're completely locked out of our buildings. But what I want to tell you about today is a recent work. It's a paper that came out a couple of days ago with Lee, who many of you know, Kyle Ritchie, who was an undergraduate student, is still an undergraduate student, just graduated from the University of New Mexico. He worked with me last summer as part of a research program for undergraduates and then kept working on it. So this project essentially started from discussing these questions with him and with my graduate student using Tang or John, and it has evolved nicely. I think we learned more than I was hoping for. So our main goal was to try to see if we could say something about non-relativistic RG flows using holography. And we were particularly interested in asking if we could figure out any general properties and also identify quantities that are monotonic under the flow. So as a basic motivation, there's a long-standing question in quantum field theory about how you can measure the number of effective degrees of freedom of a system as the energy scale of the system changes. So we have our naive intuition that tells us that as you lower the energy, you should lose degrees of freedom. But that intuition is hard to make very concrete when you have systems that break a variety of symmetry. So there's been progress in certain cases, which I'll talk about in a bit, but in general, it's a difficult question. And on the gravity side, this is related to the question of how we integrate out degrees of freedom in gravity. How do we geometrize a G-flow? There's been a lot of work on this question, and I'm not citing anyone here just because of the massive amount of work. But the main point is that this is a beautiful picture that we need to better understand, and it's a difficult picture to make very concrete in general. So this was basically our motivation. Now there's been progress on these questions. In particular, if you have relativistic field theories and somewhat special field theories, there have been cases where c-theorems have been proven. So in particular, the c-theorem tells you that you can find, in cases where this has been done, you can find a function that interpolates monotonically between central charges in the UV and in the IR. So imagine you have a flow between two CFTs. If there's a function that interpolates monotonically between the central charges, that can capture the change in the number of degrees of freedom. And I'm sure most of you are familiar with the history of this work, various conjectures, cases in which it has been proven. And apart from looking at it just from field theory, there's also been a lot of work within holography with various generalized c-theorems. The advantage of holography is that many of these results can be done in any number of dimensions. So it's a little bit less constrained. So the original papers go back to Friedman and collaborators, Girardello and collaborators, and then more recently, a lot of work by Myers, Sinha, and then Myers and Singh, and so on. But the point I want to emphasize is that all these theorems, which are beautiful and very useful, rely heavily on Lorentz invariance. And if you don't have Lorentz invariance, they break down. So we should ask whether we can extend them, or at least extend them under some set of restrictions, to cases where you may not have Lorentz invariance at all energy scales. We would like to believe that there should be a way to quantify the loss of degrees of freedom as you lower the energy, at least in some systems. And maybe this is not a general feature, but that there should be some quantum system in which that is the case. So my personal motivation for thinking about this started a few years ago when I worked with Xidong on trying to generalize the C function that had been obtained from entanglement entropy of a strip to systems that are non-relativistic. So we looked at this question, and although it's relatively easy to see that in general this function is not monotonic, it's possible to find constraints on the geometry that will make it monotonic. So that is, at least for me, was a starting point to see that maybe it is possible to say a little bit more. So I wanted to revisit this question and see if it can be, if something more can be added to this story. So going back in time, there's also been a huge amount of work on RG flow that relies heavily on the radial Hamiltonian formalism or Hamilton-Jacobi approach. This has been extremely useful to understand RG flow. And one quantity that is special in this framework, or at least valuable, is the so-called fake superpotential. So I'll come back to that in a minute, but essentially this is a quantity that allows you to recast second-order equations of motion in terms of first-order flow equations. And it's very useful to characterize the flow and also gravitational solutions. And I'll show you in a minute that it's related, at least for relativistic systems, in an easy way to the C function. So all these ideas are tied together. And I'll come back to that as well, but I was also motivated by a paper, at least a paper, a series of papers by Elias, Kiritsis, and collaborators, where they used the superpotential heavily to classify RG flows. So we were looking at that and kind of got asked if we should think about extending it. So our plan was to take this superpotential formalism and adapt it or use it to study non-relativistic solutions. And we consider Einstein-Maxwell-scalar theories, as you'll see, and also in some cases, as it turns out, our results are stronger if you drop the gauge field, not surprisingly. But we learned a lot of interesting lessons, relatively simple lessons, and identified a variety of quantities that are monotonic. So before going into our own work, I want to give you a little bit of an introduction to the role of this superpotential. So imagine that you have very simple theory, Einstein-scalar theory, with a metric that preserves Lorentz invariance of this form. And you can show that if you take Einstein's equations for the warp factor, this function A, and the scalar field, they can be turned into first order equations by introducing what's called a superpotential. So this W is a fake superpotential related to the scale factor in a particular way, it's a derivative of A. And by the way, these are radial derivatives. And if you impose that it also obeys this kind of relationship, so the derivative of W with respect to the scalar is equal to phi dot, then you can show that Einstein's equations satisfied, and you can turn the second one here into this first order equation for the superpotential. So I'm sure many of you are very familiar with this story. Just a side comment, you can also compute the beta function for the scalar, assuming that the energy scale read from the metric is of this form. And you find that the beta function depends on this derivative of W with respect to the scalar divided by W. So this superpotential determines the properties of the RG flow. Okay, so that's a little bit of a simple review, but I want to focus on the monotonic properties of this W. So it's easy to see once you define the superpotential in this manner, that it flows monotonically under radial flow. And that follows simply from the fact that the radial derivative of W is basically the kinetic energy of the scalar. So this is a very simple step. Another thing to note is that if you compute the null energy, if you assume that the matter in the theory satisfies the null energy condition, you get a constraint on the sign of A double dot. And in turn, that shows you that W dot will have to be positive. So the null energy condition ensures that W is essentially monotonic. To see the connection with the C function, I'm going to remind you that the original paper by Friedman and collaborators where they derived this, what we call the C function or the A function. That monotonic function depended on the inverse of this, the radial derivative of the scale factor. So ignoring for a second the dependence on the dimensions, you can see that the flow of this function is determined by A double dot. The radial derivative of A will be determined by A double dot, precisely in the same way in which this superpotential, the superpotential derivative depends on A double dot. So you can already see the connection between the C function and the superpotential. This is all done, of course, in a relativistic system. Now, you can see a similar story if you look at entanglement entropy and extract the C function from that. So without going into the details of this paper, I just want to point out the main feature. So Myers and Singh proposed a version of a candidate C function that you could extract by looking at entanglement entropy of a strip, an infinite strip, generalizing the work of Cassini and Huerta. So if you compute this C function, and if you compute the variation in entanglement entropy with the length of the interval, the length of the strip, you can find, after a lot of manipulations that I'm not going to go into, that the running of the C function is essentially controlled again by this A double dot. More precisely, it's an integral of this form, but the quantity that's of interest for us here is this A double dot. So again, if you impose a non-energy condition, then you get automatically that this C function is monotonic, as they pointed out. So this is another way in which you could see the relationship between all these quantities, so the superpotential, the monotonicity of the superpotential related to the monotonicity of these C functions. Okay, so our goal is to extend bits of this story. So if there are no questions, I'm now shifting to talking about our paper. So we
actually, quick question.
Yeah.
Yes. Do you know if it's enough to assume the average null energy condition?
That's a good question. The average, you mean in this case?
Yes, this one or the previous one.
The average non-energy condition. I don't know off the top of my head. I would, yeah, that's a good question. I don't know. I need to look at that. So you're thinking if you have a violation of the non-energy condition somewhere. Well, okay. So the point here is that the non-energy condition is a sufficient condition, but it's not necessary, right? So in principle, you could have violations by keeping this entire integral with the same sign. Right? Mm-hmm. So without looking at it, I don't know. And I don't know if anybody else looked at that. Maybe somebody else knows the answer. But in principle, it's possible as long as this integral is positive or negative. You know, the sign doesn't change.
Okay, thanks.
Sure. Other questions? Okay. So we looked at Einstein-Maxwell-scalar theory of this form and introduced geometries that could in principle violate Lorentz invariance by introducing this function of the radial coordinate. So you can think of F as characterizing the deviation from Lorentz invariance so that we could study flows that could be non-relativistic. But we always assumed that our geometries approach ADS at the boundary. So we want this function f of r to approach 1 in some units at the boundary. Okay, so keep that in mind. So for us, the UV is always relativistic. Okay. We wanted to work with the superpotential formalism, and for a theory that's much more complicated than ours, this was worked out by Yannis and collaborators in this paper. So we simply borrowed the results. The key ingredients for us in this case is that so you can again introduce a superpotential W. So if you look at the first line here, this is the same definition of the superpotential that you had in the previous relativistic case, but now you have additional degrees of freedom. You have this new function f of r. So what you need in order to convert Einstein's equations into first-order equations is an additional condition on the superpotential. In particular, its derivative with respect to the scale factor needs to be equal to some combination of f dot and f. And finally, this is the same condition that you had previously in the relativistic case. So this is essentially the new ingredient. And once you do that, you can turn again your second order bulk equation become first order. So if you want to see the details behind the derivation of these guys and the entire radial Hamiltonian formulation, this is a very nice paper that worked it out in glory detail for a much more complicated action. Okay, so a few things to keep in mind. So what we have here are essentially more degrees of freedom, 2 effective degrees of freedom. So we have W, but we also have this WA. So I like to think of this, I think of them as different superpotentials, although they're not, but they are related to different effective degrees of freedom. And another thing to remember is that WA is the object that encodes the breaking of Lorentz invariance. So when WA vanishes, that's when you recover the relativistic case. Another thing to...
Sera, sorry. Is
Yes.
WA the derivative of W with respect to A?
Yes.
So W is a function of 2 variables.
Right.
Okay, so it's not an independent function then WA.
It's a function of yeah, it's a function of 2 variables. That's right.
Okay.
Yeah, that's right. Another thing I think I forgot to mention it. Sorry. Oh yeah, I did mention that the beta function in this case was proportional to this W phi over W. So if you look at the beta function in our setup, you can now see that it's modified. Essentially, the energy scale is now is sensitive to both F and A. When you compute the beta function, what you get is this modified version. So the denominator has this additional dependence on WA. So from that point of view, it's easy to see why the flow will be sensitive to all the structure, including F of R.
Sera, sorry again.
Yeah.
When you break Lorentz invariance, like here, you don't
Yeah.
have a unique beta function, but you can define many. In fact, you have 2 independent beta functions. You can put independent cutoffs in space and time. So you're using a very special one here.
Right. Well, you could ask. So I think that's a good point, and we could look at more cases later. But this is basically how we proceeded. So this is step 1, what we thought about trying to do. So I'm not saying this is the only way to do it. I'm just saying this is one way to do it.
Okay.
Yeah. So I think there are many directions to extend this work and also compare to some of what you did. But this is, baby steps. So this is how we started. Okay. All right. So another thing that is to keep in mind or to note is that if you think about this value, the value of this function in the UV, it essentially sets the value of the effective speed of light there. And similarly, if you look at it in the IR, it will tell you what the speed of light in the IR is. The reason why I'm mentioning this is because it's related to a quantity that has been talked about in the literature called the index of refraction. So as far as I know, and please correct me if I'm wrong, this was introduced first in a paper by Gapser, Bufu, and Rocha, where they introduced it as simply the ratio between the values in the UV and in the IR. So think of it as the relative speed of light in the UV and in the IR. And it captures, in some sense, the renormalization of scales as you flow from the UV and the IR. This index has been studied more recently in a number of papers. by Donos, Gauntlet, and collaborators, and more work by Gauntlet with Chris Rosen and Donos and others that I didn't include, and also more recently by Hoyos and collaborators in this paper. So there's been some work on the index of refraction, but as far as I know, not too much work, in particular, not a lot about its general properties. So what we have done is study the radial flow of this function. So we elevated what we're thinking of the index as a function of the radial coordinate, which would interpolate between the UV and the IR. So we studied the radial flow, which was also done by these guys. And you can show that in this Einstein-Maxwell-scalar theory, n dot has a definite sign, and therefore n is monotonic. So I'm going to give you a little, tell you a little bit where that comes from. So obviously the first term, the temperature entropy term, is always positive. The second term can also shown to be positive. And one way to see that is that if you think about, let's choose for simplicity rho to be positive. If you look at the behavior of the radial derivative of AT is the electric field component, you can immediately see that it's positive. So this is a monotonically increasing function. So as you approach the UV, it's increasing. Moreover, in the d pi r at the horizon, it vanishes. And therefore, the fact that it's increasing in 0 DIR gives you a positive function. So the entire n dot is positive, and this quantity is monotonic in this class of theories along the flow. Okay, I don't know if that has been, Hoyos et al. Pointed out that in their particular class of examples, it was monotonic, but this is a proof that it's always valid in these theories. What the physical interpretation of this is, I don't know, but it's certainly interesting that this effective speed of light is changing monotonically. Okay. Now, if you remember how this index was defined, its radial derivative is essentially, up to some scaling, it's essentially this WA. So the monotonicity of n fixes the sign of WA, tells you that it needs to be negative. It's also easy to show that the work factor itself is monotonic. Again, assuming ADS in the UV, increasing towards the UV. So remembering that A dot was related to W, this fixes the sign of W. So in these theories, both W and WA are negative. And what that tells you, of course, is the product is positive. One place where this is relevant is if you look at the radial flow of the superpotential. So the way we have defined the superpotential, its radial flow is proportional to these two terms. The kinetic energy of the scalar, this was the term that you would get also in the relativistic case. And then this term that is spoiling the monotonicity. It spoils it because the WWA is always positive in these theories. You might think that the non-energy condition might help, but it doesn't. So you don't gain anything by looking at the non-energy condition. Okay. All right, so you can see a similar structure to this if you look at the entanglement entropy C function. So now I'm going back to my paper with Shidong from years ago, where we proposed this generalization of the C function, adopting essentially the proposal of Myers and Singh, but rederiving it or working it out for non-relativistic geometries of this form. So if you do that after some work, you can put it into the form of this integral, this is the same form that you had seen previously for the Myers result. But the thing that's interesting is that if you now try to use the non-energy condition, you can rewrite this term in this, you can essentially rewrite it in this way where we have broken it up in this particular combination because this green piece here is precisely what you would get from the non-energy condition. So this green term is positive, but then you have this other term which in principle could be negative. So you can start seeing why this C function is not going to be monotonic in general. So the non-energy condition is no longer sufficient. Now, from the analysis that we have just done, so if you remember, I just told you that this F dot and A dot are positive in this Einstein-Maxwell-scalar theory. So for these theories, the second term, F dot A dot, is always positive. There's an overall minus sign. So you always have a competition between the first term, which is constrained to be positive by the non-energy condition, and the second one, which is negative. So they're always fighting with each other. So this is exactly what you see from the flow of the superpotential, which is, of course, not surprising because that's exactly what this A double dot is. So it's just another way to see the same physics. So the superpotential, again, it's helping to recast it in a different language. Okay, so this is all I'm going to say about this, the connection to this old paper. So unless there are questions, I'm done with this part. Okay. So now let's look at the radial flow of this WA. So we find two terms. We notice this negative sign in between. It's clear that the second one, apart from the negative sign, so this piece is always positive, so this entire contribution will be negative. And the first term is always positive because we fix the signs of W and WA. So this guy is always positive. So these two pieces always have opposite signs and fight against each other. Now, if you restrict yourself to Einstein's scalar theory, so if you kill the gauge field, then you do get a monotonicity condition. You get that this WA is flowing, is monotonic in Einstein's scalar theories. So that's something. But this guy is not particularly interesting in the relativistic limit. Like, it's exactly zero. So it's not what I would think of a very useful quantity if you're interested in something that would behave like a C function and give you the answer that you expect in the relativistic limit.
Sorry, Sera, but even if you have scalar theories, you may have non-relativistic solutions, and the finite temperature black hole solutions are non-relativistic. However, right, you can still derive monotonic flows there.
So I realized, so I think you're talking about your finite temperature exotic flow paper. So your W is likely, it's not defined the same way we have W defined. So the Hamilton-Jacobi analysis of
you can do it in many different ways. All I'm saying is that this theory can have non-relativistic solutions, but there is a monotonicity.
No, that's fine. I agree. I mean, this is, are you talking about a monotonicity for W?
Necessarily, even for the scale factor. The scale factor is good enough for this, in fact.
Sure.
Yeah, but also this is true also for W.
Right. So your W is not the same as our W. So I think that's one thing that we would like to look at next. If we so how would this story change if we use your superpotential? But then another thing is that if you turn a source on, then I think you would find that your superpotential source for the scalar, your superpotential should not be monotonic. Do you agree with that?
We have sources for the scalar.
And it's still monotonic.
Anyway, let's discuss it maybe later. I just wanted to point out that you can have only scalars, but still have non-relativistic solutions.
No, that's fine. Yeah, I certainly believe that. So I'm not putting too much emphasis on this point here because this is not a quantity that we're interested in, basically. I'm just saying this is something that one can look at. It's monotonic in some cases, but we don't particularly care. The reason for that is because we want something that will reduce to the right relativistic limit. So it turns out that if you stare at these equations for long enough, you find that this combination of W and WA is actually monotonic in Einstein's scalar theory. So this particular guy is obviously positive. So this combination is monotonic. And moreover, when you approach relativistic limit, WA goes to 0 and you recover the standard result that you would have in the relativistic case. So it's more appealing. Now, Elias, we can talk about the difference between this and what you have later. But that's one of the things I would like to look at. We didn't have time. Okay. So what happens then if you turn back on the gauge field? So now you get an additional term that comes with a negative sign. So we'll spoil the monotonicity in general. So that's not ideal. However, the feature that is interesting and surprising, that we found surprising, is that if you compute this quantity, which in principle, which looks non-monotonic, for a lot of black hole solutions, it's still monotonic. I don't know why, but I'm going to show you some examples. So somehow there seems to be structure in here that it's a little bit deeper than one might think naively. Okay, so we looked at a few examples in 4D and 5D. So these are charged black hole solutions that were found long ago by Miriam and collaborators. It's a famous paper, charged black holes in ADS4 from maximal gauge supergravity. The details are not important. The main point is you have some Koch type scalar potential. You have simple exponential terms for Z, and depending on how you choose them, you can get solutions with multiple charges. Okay, so here are some plots. So for the case with one charge, we're plotting here, I'm showing you W, or rather negative W, and also the combination that we identified, which appears to be monotonic. Okay, so this plot over here simply shows you that you have multiple branches of black holes at certain temperatures. So you have what I would call a small branch down here. So these are solutions that correspond to a small horizon radius. And then you have solutions over here that correspond to larger horizon radius. So let's say small branch, large branch. Now notice that this is the quantity, this W plus WA over the number of spatial of boundary dimensions. This is the quantity that is always monotonic for Einstein's scalar theories, but also appears to be monotonic in all these solutions with a gauge field, while W is not. In particular, it's not monotonic for these class of solutions on curves that describe this small black hole branch. Okay, so this purple line and the red line are the curves are not monotonic. So that's a small branch, and it is indeed monotonic on the large black hole branch. So this is, because these solutions are known analytically, presumably one can figure out why, but they're somewhat complicated. So we haven't been able to do it yet, but I'm sure that by playing with them long enough, one can understand this behavior. Another thing, so the two charged black holes are very, very similar to this. So I'm not going to show you those results, they're in the paper. The three charged black hole is qualitatively the same, but here you have only one branch. Again, W is non-monotonic at low temperatures, this red and purple dots, which in this case is also, obviously there's only one branch, so it's small horizon radius, and then becomes monotonic. And this nice combination that we like is always monotonic. So that is the same qualitative features. We also have looked at some black hole solutions in 5D. These are solutions to the STU model for particular choices of charges. The Wolf, Kapser, and Rosen took two of the charges to be equal. I'm not telling you any of the details of the paper, but again, we find similar features. The one charge case, you see again this small black hole branch with a non-monotonic W, and in the large black hole branch, W is monotonic, and our favorite combination is always monotonic. For the two black hole, two charge case in this example, there's only one branch. This purple dot is the 0 temperature line. Here W is not monotonic, eventually becomes monotonic at higher temperature. So I don't know if anybody has any comments on this. That would be useful if there was some better understanding of why this is happening. But this quantity that you would expect to change sign doesn't for a lot of black hole solutions, even though that yes.
Can you identify the critical temperature of the phase transition here? Because usually when you have the small and large black holes, you have also phase transition. So I'm just wondering that, like in your equation of a state as a temperature as a function of R edge,
right?
If you can identify the critical temperature there to see where, if it's related to this phase transition.
So I think that would be very interesting. We haven't done that, but I think that's a natural thing to try to do. Yeah.
Thank you.
No, thank you. Okay. All right, then I went a little faster than I thought. This is the first time I talk about these papers. Okay, so let me finish by mentioning that you might ask if you could say anything generic about when you might expect this quantity to stop being monotonic. So this W plus 1 over dWA. So one thing that one can do is look at the UV behavior of the solutions. So do a UV expansion and then ask, just study when this function changes sign. So you could do that. So here I'm just listing the boundary expansions of the scalar, gauge field, and so on, the leading terms. The radial flow of this quantity will depend on a few bits. Turns out that the first one is subleading, so we don't need to worry about that. So essentially, we're looking at the competition between the second term and the last term, where the last one, so this overall constants are positive, so we really need to ask when this term will dominate over that one. So remember that we had identified that this function is positive. So this happens, so the radial flow of this combination becomes negative in a particular range of the scaling dimension. So you can show that this happens when delta plus becomes greater than d minus 1 for the case in which you don't have a source. Okay, so this is the case where phi sub s is 0. You only have the bev. With a source, instead, the leading contributions are positive, so this analysis doesn't help. And of course, what you need to do is look at the entire flow. But at least this gives you some guidance as to when you could expect this monotonicity to break down. Okay, so I'm sorry that this was a little fast, but just to summarize, so we found some features that are generic. Maybe some of them are obvious. Certainly they weren't too obvious to us. They're relatively simple. But we also found quantities that are monotonic under radial flow. And we have stronger constraints for Einstein-scalar theories, but we still have identified some that are monotonic for Einstein-Maxwell-scalar theories. Now, this is only a first step. There are plenty of directions that can be looked at. The main question, of course, is what is the physical interpretation of these quantities? There are many things that are monotonic, so what? You need to understand what they mean. Do they have a fundamental origin? And if we want to connect them to some C function or a possible C function, we certainly need to understand what they represent physically. One thing that I'm wondering is whether there is any way to interpret any of these results using entanglement. So if anybody has any thoughts on that, please let me know. Also, we have done this analysis breaking relativistic symmetry, but one could think about generalizing it to more broken symmetries. You can also ask about the role of phase transitions. As Elias already hinted at, there are many things that are monotonic. There are also different ways to define the superpotentials. So one is to understand what do you gain by using one versus the other. And I think this goes back to the main question is what is the physical interpretation of these objects? And finally, this boomerang RG flow. So these are flows that start from ADS and go back to the same ADS. These are very interesting for a number of reasons. They're also nice toy models for understanding RG flow. They're also interesting because they often, well, in the cases that have been looked at by Gauntlet and collaborators, they managed to go through some intermediate scaling regime, hyperscaling violating non-relativistic scaling regime, which is even more interesting. So it would be nice to be able to test some of our combinations of superpotentials on those flows. The problem is that the matter that you need to obtain those flows is much more complicated, and we don't have a setup to do that yet. So it would be interesting to be able to do it. So there are a lot of open questions, but I think it's a good sign that even when you don't have Lorentz invariance, some of the intuition that you had in the relativistic case is surviving. There's more structure, but there seems to be that you can try to generalize results and you can make a little bit of progress, which is good. So I'm interested and excited about this. So thank you.
Okay, with many thanks to Sera for her nice talk. We have time for, we have enough time for questions. Any question or comment?
I have a question.
Yes.
Oh, please.
The reason that you cannot make a statement right now about the boomerang flows, is it because they have several scalars?
Yeah, they have several scalars, that's right. Yeah, so I'm not saying it's not possible, I'm just saying, yeah, I don't, we need to see if you can develop the superpotential formalism for that type of matter action. So have you looked at that?
Well, not in that respect, but the people who did that, of course, they proposed a monotonicity property, which is in fact about the speed of light, something that's known since long time ago, and this so far works. However,
you're thinking of Gauntlet and
yes.
Yeah. So they have, I think they looked mostly at the index of refraction as a function of their deformation parameter. Right?
No, I think well, it's some time now because I discussed it extensively with Chris Rosen. But I think if you follow it across the flow, it is monotonic as it is in your case. But I have to check that.
Well, yeah, so I think that's a good, so we looked at some other papers and we only saw that they were tracking the flow as a function of the parameter they need. There's some deformation parameter in the theory that they use to engineer these flows. They don't have, I don't think they talk about the radial flow of n, but I could be wrong.
Anyway, I may not remember well, but this is in a sense, well, of course. Anyway, let's not discuss it because also I'm not 100% sure.
But I certainly, so I know that they have statements about monotonicity. Yeah, I think it's slightly different, but it's something that I want to look at more.
I should say that using a superpotential that is a function of phi and a has a kind of ambiguity, which is the same that you have when you try to define superpotentials for many scalars. These, of course, are known issues. And the reason is that you are following a one parameter flow, which is usually the types of flow we're following, with a multi-parameter type of superpotential. And in fact, it is known in the case of multi-scalar flows that there may be different superpotentials that may describe the same class of flows. Now, this creates an even bigger ambiguity in what the beta function does. Of course, a beta function is well known to be a scheme-dependent object, but in that case, you have even bigger ambiguity. And I don't think it's quite settled how to use this type of thing to really track the flows in the way we track them in quantum field theory.
But is it known how to relate those different beta functions to this multi to the superpotential that depends on multiple.
In concrete examples, you can. In fact, the first time that people derived the first order formalism for non-relativistic flows, we did it before Yanis Papadimitriou and company earlier for a different reason, which I can tell you later on, it's not important. But we used a one parameter family of flows instead of two. What they do is apparently more richer, but if you take any concrete example, you can always also map it into a one parameter family type of superpotentials. That can always be done. So if you have specific solutions, you can always match to the different types of schemes.
Right.
The difficulty, on the other hand, with these multi-superpotential schemes is that although eventually you can decide to agree with your fellow holographers, it would be very difficult to tell somebody who does lattice what to do. That's the problem, which is something that eventually we have to address.
Right. Yeah. Yes. What about this? Okay, so, but this function, this combination, W plus 1 over dWA, does that ring a bell to you in the language of what you've been doing? I mean, do you recognize it in any way?
No, but of course, this is a too quick answer. But I have a related comment here. And, you know, I've been playing with related issues for more than 10 years. And one thing I sort of learned by osmosis is that the source of all useful such functions is the analog of the free energy that one can compute from the all shell action. The only problem with that, which doesn't make the solution automatic, is that if you want something that interpolates between UV and IR, you have to renormalize both in the UV and the IR. That is, you have to subtract infrared divergences and UV divergences. And that's where the devil is. If you look at, let's say, in the known cases where the problems arise is precisely in this type of issue. However, if you manage to control this, that is, if you control these things, you can define, in fact, in several cases, many functions. So what I would suspect here is that probably one would have to go back, look at the structure of your effective action. And there maybe you'll get an idea about what may be the best parameters to follow.
Right.
We can discuss more about this offline if you wish, but
Sure.
That's at least my general feeling.
Okay, thank you. Any other questions?
I have a question on field theory approaches to proving things like this. I don't know if you've thought about this much. But so for example, the Komargodski-Schwimmer proof uses some kind of positivity and effective field theories of dilitons. And you could imagine writing down similar effective field theories for non-relativistic systems. Do you know if anyone has tried, or have you thought about this?
I haven't looked at that. I think it's a very good question. I don't know if anybody has tried. I mean, it seems like the natural thing to do. I would think Komargodski would have thought about it, but I don't know. Yeah, I don't know of any work, but that doesn't mean that it hasn't been tried.
I see. And the entanglement people, they also didn't try to generalize?
No, so okay, so the entanglement people, yeah, so I don't know of any, so you're thinking purely from the entanglement point of view, forgetting about gravity. I mean,
yeah,
forgetting
because
about
you
a lot
need part type approaches, maybe.
Yeah, so this is why I put it as an open question. I would love to hear, I should talk to some of the entanglement people and ask if this rings a bell. So when the last time that I thought about that directly was when I was writing the paper with She, but that was a few years ago, so a long time ago. So that's another good question, but I don't know right now if there's any obvious entanglement property that would translate into this.
Am I allowed to comment on Luca's questions?
Of course. No, Elias, you're not allowed. You're forbidden.
Luca, the method of Komargodski and Schwimmer using effective field theory is very good at proving the weak form, let's say, of a c-theorem. That is, that the ultraviolet value is larger than the infrared value. But it's not very good, or at least I don't see how it can be used to give you a function that continuously interpolates between the UV and the IR. And as far as I'm concerned, I think outside holography, where we have W, I don't think such a function has been defined in 4 dimensions. That's my first comment. And therefore, if you want something that interpolates, then probably you will have to do something more, precisely because an effective theory cannot cover the whole flow from UV to IR.
I see. Yeah.
Right.
But that's also part of why I asked about the ANEC, because I'm wondering if it's too much to ask for a function that's, you know, always positive. So of course, you know, the fact that it's positive guarantees
when you ask about ANEC, because in that case, it depends what you are allowing. If your couplings are constant, because if your couplings are space-time dependent, then it's not even clear whether in that case you might expect a c-theorem anyway. Mm-hmm. But if your couplings are constant, then the only way that you can talk about an average ANEC is along the radial direction. Is that what you have in mind?
Right, yeah.
This, I think, is an interesting question, and to my knowledge, it has not been explored, but it may be interesting to check.
Okay.
Sorry, I have a comment on the first comment by Elias. So what is the physical reason why we want this function to go monotonously down? I mean, I understand the physics that the degrees of freedom in the IR should be less than in the UV, but why these things should go monotonically and not up and down, for example?
Well, I mean, you're integrating out degrees of freedom, right? You would like that process to be monotonic.
My only understanding of this is it's because you can. Of course, it may be enough information for you that some quantity in a CFT, in the UV CFT, is bigger than a quantity in the IR CFT. But if you want, and that was why I think Zamolodchikov's c-theorem also made an impact, but if you want to interpret this as a continuous, let's say, decoupling of states along the normalization group flow, then you need something that's monotonic along the flow. There is, however, also something to remember that as proven, in fact, explicitly by looking at stress tensor correlations, etc., by, I think, Friedan and company, if there is a monotonic C function, there is an infinite number of different monotonic C functions. So the C function, if it exists, is not unique. There are different measures, if you wish, to track this, and there might be many different types that you can define.
Okay.
So perhaps can I ask a simple question? So how much more constraining are the sufficient conditions compared to the necessary ones? Have you looked at this?
Which type of what conditions are you thinking of?
Of the C function conditions, right? These are the sufficient ones, right? It's not the necessary ones. This is also related to the average null energy condition that you have.
Right, yes. So are you thinking the null energy condition being sufficient? And not necessary? Yeah. So the statement is that it's sufficient but not necessary. So from the point of view of this entanglement entropy calculation, so the whole point of, sorry, let me move I can't see my own screen. So the whole point of this paper, well, part of the point of this paper was to find additional constraints that would make this C function monotonic. So we identified a set of constraints on the geometry in the UV that would guarantee a monotonic flow. So you could do that, you could play those games, but they're not general, they're not going to be valid in general, and then you need to understand what they mean physically for the solutions that you're looking at. So yeah, if you look at this paper, we discussed constraints that would make this quantity.
Yeah, so exactly here, the necessity are much more generic, right? That was I was.
The what?
The necessary conditions are much more generic. They're not so much constraining.
Well,
Yeah, so you integrate over, and you take the integrand to be positive. Okay. So this is the necessary. This is something that you need, right? But necessary is much more generic condition. It can go up and down, this integrand.
Yeah, so this is related to what Luca was thinking about. Yeah. So we looked at it a little bit in this paper for this particular function, but not more recently.
Okay, thank you.
Okay.
May I ask one more question?
Sure.
So I'm not in this community, so if the question is too stupid, sorry. But I was wondering if something like this C function theorem or something like that has been studied in JT gravity, like for two.
Yeah, so I think some of that has been looked at, but I honestly don't know. I haven't followed that much, so I can't tell you. I know there's been work, but I can't really give you an intelligent answer. Maybe somebody else can, but I haven't followed it.
Some of your formulas cannot be extended, cannot be used in the 2D gravity, right? And some of them can be used, or then.
Yeah, so this is basically all we're assuming.
Yeah.
Yeah, so I think that, there has been.
I think in general, this doesn't work in 2 dimensions.
The what?
You have to study it differently.
Yeah, but I think there are people looking at these flows. I don't know. I shouldn't comment on it.
Sorry, I had a question. Maybe you said at the beginning, but I missed the first part of the talk. If you could comment, there was a recent paper by Hoyos, Nico Jokela, and so on, and their kind of message there is a bit negative on this entropic C-theorem for non-relativistic theory. I don't know if
I looked at bits of that paper for the particular things that we were interested in. So in general, these flows are in general. So it's difficult to find quantities that are generically monotonic. So one thing that we found is this effective speed of light. It's this so-called index of refraction. In this theory, this is monotonic. But in general, the other things, it's easy to see that there are deviations from monotonicity that come from the breaking of Lorentz invariance. But I think what they did is, what we're doing is different. We're using this square potential formalism to try to say something more. So I don't think they looked at that in their paper. They looked at.
We're looking at the entanglement entropy. Constructing C function from entanglement entropy.
Yeah, so I'm not surprised. So this, you can already see from here why if they're taking the sort of this type of construction of the entanglement entropy, the C function from entanglement entropy, you can already see why generically it's not monotonic. It's easy to see that. People know that. So, you can hope to constrain it, but in general, it's not going to be, because you have this competition between terms of which one is always positive and one can be negative. So so that's not too surprising.
Okay, thanks.
You're welcome.
Okay, any other question or comment? Good. So let's thank again Sera, and I would also like to, you're welcome. Thank all you for joining us. And as the last point, let me mention that, let me bring your attention to the unusual time of our next week webinar. It will be at 18 instead of 16, and hope to see you all next week. Goodbye.
Thank you. Bye.